This is a collaboration series with Aspen Tech. For more information, stay tuned until the end of this video. Hi there, nice to see you back in this video series in which we are exploring the electrolyzer models. Now, please keep in mind that this is video number 3, in which we are going to be covering all the theoretical concepts that are required to understand the unit operation. And if you missed video number 1, in which we cover hydrogen economy, and video number 2, in which we cover the specifics of hydrogen technologies, ensure to check them out. Because the intent of these videos is to make much more easier the transition to the simulation and how to use the electrolyzer model in Aspen Tech software. So without further ado, let's continue. And guys, we prepared this presentation for you. It's going to be available in the description so you can download it and get to understand all the fundamentals of the proton exchange membrane electrolyzer model for Aspen Tech software simulations. It's going to be mostly based on the proton exchange membrane electrolyzer, but more importantly, we're going to be covering the theory and fundamentals for process simulation, meaning that we are not going to be covering right now on how we can do the simulation, rather what are all the theoretical concepts that are required to understand how to simulate such unit operations. And truth be told, guys, is that this lecture is going to be technical with respect to electrolysis, so it may be good for new students or people that it's not quite acquainted with the topic. But if you are someone that already knows about electrolysis, already knows how to simulate electrolyzers, you can skip to the next video in which we're going to be jumping directly into the actual software. If not, stick with me. This is the agenda of today. We're going to get started with a very brief review on electrolysis, more importantly, a focus on the cell model, mass transfer, limitations, thermodynamics, and the so-called overpotentials. So let's get started with the review. Now, we already covered a lot of this in the previous video about the electrolysis of water, so we're not getting to get that technical. So just remember that in the electrolysis of water, the main goal is to obtain hydrogen gas, which is a very valuable fuel. And of course, we obtain the oxygen as a byproduct. Now we're going to be focusing our attention mostly into the PEM electrolyzer, which stands for proton exchange membrane, and as the name implies, we're going to be using a membrane which allows only protons. Remember, protons, it's a fancy word for the ion of hydrogen, which has lost its electrons. And the interesting part right here is that the membrane is going to facilitate the hydrogen flow, and it's going to be easier to form the hydrogen gas. Here are the anode and cathode reaction, as well as the total reaction, guys. This is also something that we cover in the production section of the last video, how a PEM electrolyzer will look in real life, and of course the process flow diagram. So what we have here is the inlet of water, and we got the DC supply directly to the electrolyzer. The electrolyzer is going to be forming oxygen gas, separating all the other relevant material, and we got a separator which is going to be removing or separating the hydrogen gas. Now, these are the reactions on the electrolysis of water, and of course these variables that are important if you are not familiar with them. Avogadro's number, essentially the total number of molecules per mole, or the total amount of electrons per mole. The charge of a single electron, you can see it's quite low compared to the 23 here, and Faraday's constant, which is nothing more than the product of these two aspects, totaling a 96,485 coulombs per mole. And remember that ampere per second is nothing more than coulombs per second times second, so they cancel each other. An important factor, because we're going to be considering power later on. Remember, power is nothing more than current and voltage. And now let's get started with the actual study of the cell, so the so-called cell model. I have this diagram right here, and I think it really helps to imagine the cell. The cell essentially is this part right here, which is the channel, which we are going to be abbreviating as CH. We got the left-hand side, which is the anode side, and the cathode side. More importantly, we have the electrodes, the anode electrode and the cathode electrode. And of course, we cannot miss the membrane. The thickness are important, are quite relevant for geometry. We're going to see that later on. But for now, I want to show you that there is a flow of feedstock and a flow of product, depending on the location. One of the main questions when you are modeling, especially when you are working with a product like Aspen Plus, is which unit operation could be similar to the operation that we are using. And back in the day, they used to model this as a reactor, a continuous stir tank reactor, because the assumptions of continuous flow was on point, they are perfectly mixed, and they operate in steady state, which is pretty similar to the operation that we have in the electrolyzer. Now continuing, as stated before, these are the main parts, and later on we're going to see how to fill up the input data for the electrolyzer. But for now, it is important to understand what is the fundamentals, what is the science behind all this. And geometry is going to be affecting the following. Number one, current density. So of course we know that the area of exchange or reaction, let it be, is going to be affected, and of course the thickness of the membrane and the electrodes. Not only that, guys, we are going to account for pressure drop. Remember that the more barriers we add, we are going to encounter more pressure drop. That's just natural. Also, we're going to encounter loss of current or the ohmic resistance due to membrane, electrode, and plates. Also, we have some diffusion layer aspects to consider. We're going to see that in the mass transfer part, make no worries, and some recombination reactions. Moreover, guys, I really want to focus my attention in the mass and energy balances. And these are based on this diagram right here. So we get the inlet of moles, the outlet of moles, more important, the SRC, which we are going to focus our attention right now. Another important factor is the total amount of mole flow crossing through the membrane and the recombination reaction, which should be a small number. So the main focus of our attention should be SRC, which is the total amount of material being reacted or generated, and the total amount of moles crossing. Now the energy balance is pretty straightforward. It's the difference in enthalpies from the left and right hand side, or in and out. Then we got the duty to the unit. More importantly, power, which we already know depends directly on the current and the voltage. Now, what is the so-called SRC term? And we can define it as the rate of change. It typically refers to how fast the concentration of hydrogen or oxygen is changing inside the electrolyzer. That's straightforward. So it's a rate of reaction. Now, this is quite similar to the rate of reaction used in chemical reactors. So the change of moles per change of time in a given volume. But in this specific case, it's going to be more a rate of reaction with respect to the electric charge. So you can see how this is going to be helping us to analyze how the electricity that we are passing through is going to be increasing or decreasing, maybe maintaining or stagnating the production of our desired products. And then, as stated, we have some pressure drop calculations. These are pretty similar as we dealt with fluid mechanics. So we have a change in pressure divided by density equals, or is related to the half of the square of the velocity. And actually you can see this right here. Now, of course, because we are talking about other unit operation, we need to add a factor of correction for the plates, the membranes, and the channels, and of course the friction lost through all these units. Now, of course, we already understand that this is definitely a mass transfer problem in which we are going to encounter that, yes, there are certain type of limitations regarding mass transfer. Of course, we're talking about diffusion or diffusivity, the concentration profiles, water drag, and other concepts. So first things first, let us talk about concentration. Mass transport will allow us to model concentration profile and gradients. So that's great. I'm pretty sure that you are quite familiar with this diagram right here, in which we have a low concentration to high concentration gradients. The same is true for the reactants and reverse. Yeah, we understand this theoretical, but actually how are we going to model such concentration profiles? So this is what we're going to see right here. Recall that there are two main points of interest right here, guys. We require to calculate, yes, the total amount being produced, but also the total amount of moles actually crossing the membrane. So in one specific case, we have the cathode, which is the water, technically speaking, the solvent and reactant. And of course, we will have a amount or concentration of oxygen gas. The same is true for hydrogen gas, and the reverse could be said for the anode. We have concentration of oxygen and hydrogen. Let us explore a little bit more this diagram right here. And as you can see from the membranes, we are going to encounter the highest amount of values. So actually, when we go to the electrode, we're going to see that we are going to be producing oxygen. At this point right here is going to be the maximum amount of oxygen. And of course, it's going to be diluted in water, which is the solvent, and eventually we have our final concentration of oxygen gas, which later on is going to be separated and converted into oxygen gas. The same is true with hydrogen. We have the maximum amount of hydrogen after the membrane allows for the proton exchange. So hydrogen is going to be diluted in water, and eventually it's going to be separated into hydrogen gas. We can also and must account for the changes of water concentrations, which kind of sounds very repetitive, that this is the solvent and the reactant, but definitely something that must be done. As you can see, guys, we have a specific model right here for the total amount of moles being crossed in the membrane. And actually, we're going to be exploring these concepts later on. This is the area of the membrane, the porosity of the membrane, then we have the diffusion of species I, and then the size of the species. Afterwards, we account for the change in concentration, which is the driving force accounting for the crossing of the hydrogen. And of course, these are based in the following models, guys, in binary diffusion and Knudsen diffusivity. And of course, these are based in these models, guys, in binary diffusivity and Knudsen model, which is going to be working accordingly to the PEM concentrations in the membrane and in the channel. So remember that M stands for membrane, CH stands for the channel, and this one right here is the change in concentration due to the mass transfer. Okay, so that was for hydrogen, but we gotta do this also for the solvent, which is water. And as you can see, this is quite dominant because, well, it's water. It's going to be the solvent across all the environment. And we gotta ensure that we work with diffusion. We gotta ensure that we are accounting for the electroosmotic drag, also known simply as osmotic drag. And then we have this specific equation. So yeah, diffusivity of water, the drag of water, and the pressure of water. And for the given equation, guys, of the total amount of water crossing through the membrane, we're going to be focusing our attention right now into the diff concept, which is actually diffusion or the diffusivity of water. And actually, guys, this is pretty similar to fixed model with the adjustment of temperatures. We have an initial value for the diffusivity at standard conditions. Then of course we need to account for the ideal gas constant and the energy of diffusivity, the changes in temperature. And this value right here is typically given, depends on the substance in which you are going to be making the diffusion. Some quick notes, guys. Pretty sure that you may or not be quite familiar with water drag. So essentially, in the context of a proton exchange membrane, we're talking about the phenomenon in which water molecules are actually dragged along with the generated hydrogen gas during the electrolysis process. So it's pretty similar. We have some, try to imagine like a wind of current, not air, let it be hydrogen gas. And yeah, this is physically moving or dragging some amount of water. You can imagine that this is the main idea of water drag. So yes, the higher velocities, we may encounter more water drag. Secondly, the electroosmotic drag refers to something pretty similar, actually refers to the movement of water molecules through the proton exchange membrane. Finally, the hydraulic pressure effect, which refers to how changes in pressure, let it be delta P, can influence the gas phase mass transfer, gas dissolution, membrane performance, and generally speaking, the electrolyzer efficiency. So yes, these are the concepts that we are studying right here: the diffusivity, the drag, and the changes in pressure. Another important aspect, guys, is the rate of oxygen. There are certain limitations because, as you can imagine, oxygen is quite flammable and, well, quite explosive. So there will be some limits to the production of oxygen. Remember that actually we are going from liquid phase of water into gaseous phase. So this is also a huge change in volume. So that's why we're going to encounter that the oxygen production is limited due to specific limitations of operational safety. So now you know more about the mass transfer limitations for the electrolysis of water. So now let us continue with thermodynamics and electrochemistry that goes behind the cell. And of course, as you can imagine, we're going to be talking about Gibbs energy, cell voltage, and cell potential, which are the main fundamentals whenever we talk about electrolysis. So first things first, let us recall that the Gibbs free energy will allow us to understand whether or not a reaction is going to favor. And not only that, it's going to give us some parameters, objective numerical data that will let us know what are the required conditions to go in the, let it be, forward direction. In the specific case for cells, we know that the change in Gibbs energy of such cell is given as follows. So yeah, we have some temperature changes, entropy in the cell, and enthalpy. Moreover, we know that in standard conditions, we can relate the total amount of moles being interchanged the Faraday's constant, and the cell potential in standard conditions. Not only that, the cell potential for the electrolysis of water is given as follows, guys. So yeah, remember that negative values implies that these are naturally occurring as long as you add electricity. And the change of energy per unit mole of hydrogen required to go in the forward direction. Now let's talk about current density. As you may imagine, this is the total amount of electrons flowing per unit area, per unit time. And typically speaking, there is a minimum limit in order to ensure that there will be a reaction. But of course, typically speaking, at industrial levels, you don't want to work in the minimum amount of value. You want to work in the best efficiency point. So what we're going to encounter is that, yes, remember that this number right here, 1.23, is the equilibrium reaction, meaning that anything less than this will not favor the reaction. But if you go into higher amounts, you're going to be producing much more oxygen gas and the hydrogen gas right here. And essentially, this is saying that the more current density we have, the more hydrogen gas and oxygen gas will be produced. And finally, guys, we were talking about the energy balance. I'm pretty sure that you are familiar with this equation. Well, this is pretty straightforward. You can ignore this right now, and the duty can be ignored. We're going to be focusing our attention into power, which we already know that the power is given by the current, which is related towards the density, current density, and the voltage. So of course we need excess voltage that must be applied to the cell or electrode to drive the reaction to a certain rate. Pretty good time to introduce the idea or the concept of overpotential, which is also known as polarization, and we're going to be using the variable, Greek variable eta. So essentially, overpotential, as the name implies, is the extra potential that you are adding into this cell. So yeah, we got the potential of the cell, which is essentially the standard difference of these two, and the polarization. So when we add the total amount of excess voltage, also known as overpotentials or polarization, we're going to be adding the sum of all the overpotentials from the hydrogen evolution reaction and the oxygen evolution reaction. You are going to account that the total amount of overpotential for the given cell will be that of the overpotential of the activity, overpotential of the ohmic resistance, and overpotential of the concentration, which is driven by the mass transfer. And now we go to overpotential, guys. We made a very brief introduction in the previous slide. We're going to be talking about what is the so-called overpotential overall performance. So as stated, guys, we have this value, which technically speaking is the sum of all the overpotentials or the so-called polarization of the cell. We have three main issues going on. Number one will be the activation overpotential, which is this one right here. Number two is the ohmic loss. And finally, the concentration or mass transport loss, which is going to be one of the most important ones. We're going to see why. Before I continue and explain these ones individually, we're going to understand that the cell voltage is essentially what's going to be measuring the so-called overpotential. And this yellow line is the total addition, this value right here, of these three concepts. Number one, activation overpotential is right here, the activation losses. So as you can see here, it's going to be maintaining a almost constant value. Of course, it increases, but generally speaking, the activation loss is just that loss at the activation of the reaction. So we could say that this is a fixed value. Secondly, the ohmic loss, you can see this red line right here. This is a straight line, very proportional to the voltage or the overpotential. So meaning that the more overpotential you have, you're going to have a linear interaction. More importantly, the one that we want to explore the most is the mass transfer loss, which is this one green right here. And what I want to see is that the further you go into the reaction or the forward direction, you're going to encounter that you require more flow or more voltage in order to account for the mass transfer loss. So yes, technically speaking, the mass transfer is going to typically limit our reaction. And we're going to see why in the next slides. So yeah, let us fully define the activation overpotential. So yeah, as you can imagine, it is quite related to the minimum activation energy for the reaction to go in the forward direction, meaning into the production of hydrogen gas and oxygen gas. We're going to be modeling this with the Butler-Volmer equation, which I don't want to get that technical. We can do so in later videos in the series, but essentially is the fundamental equation in electrochemistry, that describes the kinetics of electrochemical reactions occurring in the electrode surfaces. It typically relates the rate of an electrochemical reaction to the electrode potential and the properties of the reaction. So yeah, these are the equations. And as you can see, it depends on the temperature, the ideal gas Faraday's constant. It also depends on the Gibbs free energy of activation. Also accounts for temperature not being that of the reference. There you have it. That is the activation over potential. As stated before, it's going to be a fixed value. As we also saw, it is an exponential natural logarithm. So it's going to be fixed at very high amounts of the reaction. Then we have ohmic overpotential, guys. As the name implies, these are the losses due to resistance. Remember that anything that conduces electricity will encounter a resistance for electrons to flow. So this so-called resistance is going to be accounted here. We need to account for the resistance of the cell, the resistance of the electrodes, the resistance of the plate, the resistance of the membrane, and of course some inefficiencies, the resistance due to fall. It depends on the membrane resistance. Of course, you're going to see later on that there's a whole world of membrane materials. We're not talking about the PEM electrolysis models. And typically we're going to be choosing those of polymer properties. They are going to be affected by the degree of hydration of such unit operation. Finally, yet not less important, we have the concentration or mass transport limits. This overpotential is typically associated with the concentration gradients. And yeah, we're going to be using a Fick's law, which is typically related towards the concentration changes, the driving force of mass transfer, and Nernst's equation, which relate electricity and reactions. So very quickly, we have a simplified version, which is this one right here. Let me explain it. We have the ideal gas constant, we have the temperature of the cell, we have Faraday's constant, and of course, let me dissect this value right here. So M stands for membrane, CH stands for the channel. Then the EAN stands for anode, and the O2 stands for the species that we're talking about. This will be oxygen, of course, but later on we're going to account for the hydrogen value, which is going to be in the cathode membrane, and the hydrogen value that is going to be in the cathode, but in the channeling. So yes, this is how we are going to be evaluating the overpotential for the mass transfer, which we already know is the main limiting factor whenever trying to go in the forward direction. So there you have it. This was a lecture that definitely went very deep into how to model a electrolyzer, either manually with spreadsheet or eventually with a process simulator. Now, of course, before we continue to the next video, we'd really love to know what you think, guys. What are your main doubts or concerns that you may want to ask us before we dive in directly into the simulation of a electrolyzer? Remember that in that demo session, we're going to be exploring the minimum input for the unit operation or the model in Aspen Plus. We're going to be exploring what are the typical results that we may obtain. We're going to be making the so-called sensitivity analysis, in which we change certain variables and we see how it affects other type of variables, typically how the voltage affects mass transfer, the total amount of oxygen and hydrogen being produced, and many other aspects. So guys, please let us know in the comment section all the questions and comments you would love to see cleared out in the next session. On our behalf, that will be it, guys. We'll see you in the next video.